Hello everyone. So welcome to this 12th week of interaction session on the course on robotics, basics and selected advanced concepts. So this is the last week when we are meeting and we are looking into more of the content on deployable structures, right? So we'll see few of these, but before that, what we have done entirely in the course, I would like to recapitulate that, and then I think it would be easier for me to move to the last topic that we have today. Um, I don't know, right now we just have one participant. Hopefully, in some time, we get more number of participants. If we don't have, this video is anyway going to be uploaded on YouTube, and from there, you always have the access. So from there you can watch the videos, you can watch the questions, and then you can think that how you're going to solve all of them in the assignments, right? So I think that is perfectly doable. Let's start with what all we have covered. So just exams are very close, and I think we should understand what all we have done. So if you remember week 1, it was when we were pretty new to this topic, so not new to robotics of course, but then new to this course, and then we started right from very basics, where we wanted to introduce where we wanted to introduce you to robotics, from where it comes, okay, and then what are the types of robots, what are the main elements of a robot, what is called link, what is called joint, how do we model and do analysis of robot, like modeling and analysis part of robot, right? When we understood, so it was just very basic modeling. Once we came to know about all of these, we moved to DH convention, right? There were some mathematical preliminaries where we learned about homogeneous transformations, and then we again reiterated more on joints and links, and there were examples of DH parameters and link transformation matrices. All of them we got to see in our second week. Third week started with kinematics of serial robots. So until now we are always doing serial robots. We just had seen types of parallel robots in the first week. But in kinematics of serial robots, we saw direct kinematics, we saw inverse kinematics. We came to know what is the difference between them, and which and how this inverse kinematics is difficult to solve. We often don't end up at a unique solution. Okay, so all of them we covered when we were talking about inverse kinematics of serial robots. Then we also saw inverse kinematics with of serial robots with the number of links less than 6 and greater than 6, and how they are different. We learned about what is elimination theory, what are the solution of nonlinear equations, and we also saw inverse kinematics problem for general 6R robot, right? So this is how we covered kinematics for serial robots. Then we also moved to parallel robots for the first time. We saw what are loop closure equations. If there is a 4-bar linkage mechanism, how are we going to define active links, passive links, and active joints and passive joints, right? How we are going to break the loop. All of those came right in the kinematics of parallel robots. And then we also saw direct kinematics of inverse of parallel robots, and then inverse kinematics of parallel robots. There we saw the parallel robots. If we're dealing with inverse kinematics of parallel robots, it is relatively easier and simpler, right? Then we also saw what is the mobility of parallel robots. So all of them. And at the end of this week, I think we moved to direct kinematics of Stewart platform manipulators, right? So we did that. Once we uh, did that, then we moved to some applications of parallel robots, where there were many experiments demonstrated from right from ISC Bangalore lab, right? There was a sun tracking robot, so it was made using a 3-DOF parallel manipulator. And then we also saw Stewart core platform based force torque sensor. So after this we also did vibration isolation using a Stewart core platform. Then I think we dealt with um, this thing. Yeah, we dealt with velocity analysis of velocity and static analysis of manipulators, where we saw what is linear and angular velocity of the links. Then we saw what is serial manipulator Jacobian matrix, what is parallel manipulator Jacobian matrix, how they are different, and then we also saw what are the singularities in serial and parallel manipulators, right? Then we moved to statics of serial manipulators and for parallel manipulators as well, but we haven't yet come to dynamics, right? Then in week 7, we saw uh, what are hyper redundant robots, what is redundancy resolution in a human arm, and we also had a lecture on flexible robots, right? And we saw that what are the various methods of modeling these uh, flexible robots, right? Then in week 8, we saw Lagrangian formulation. Why? Because we wanted to formulate the dynamics of serial and parallel robots. We saw what are the equations of motion, right? And then we saw what are the inverse dynamics and simulation of equation of motion. How do we do that? And then we also saw some recursive formulation of dynamics of manipulators. So all of them was covered in week 8. In week 9, we switched gears, we moved to control. That was a basic control, that was just linear control. So we saw how do we plan the motion, how do we fit, if we're given the start point, end point, and some initial conditions, or let's say some velocities, then we are able to fit a curve. So all of them we saw the simple PID control of multi-link serial manipulator and how do we do it. So it was just linear control methods. Whereas in week 10, we moved to non-linear control, right? So there we saw how do we control a multi-link manipulator, and if there is a constrained or a parallel manipulator, then how do we do the Cartesian control? Uh, how do we control them, and how do we do the Cartesian control of serial manipulators? We also saw a force control of manipulators here, right? So we also saw in the later part we saw what is hybrid position force control of manipulators, if position and force both have to be controlled. So there we dealt with some advanced topic in non-linear control of manipulators, right? We saw the Lyapunov's method as well. Then in week 11, we moved to wheeled mobile robots. Now we were away from manipulators and we thought that we should also read about wheeled mobile robots. So last time only I think this was covered. Okay, so where we saw how are wheeled mobile robots uh, simulated on a flat terrain, how on an uneven terrain, how do we even simulate uneven terrain, and what are the kinematics and dynamics of this WMRs on uneven terrain, right? Then in the last week, we learned about over-constrained mechanisms and deployable structures. So there we learned, this is the day today, we are going to do it. But we are learning about over-constrained mechanism and deployable structure, and we are also going to see the kinematic and dynamic analysis for each of them, right? So the most important book, I hope you have it. Uh, so if you want to study any of these topics in detail, I think we had discussed on the first day, and today we are discussing on the last day as well. You can always go through this book. It has the topics even more detail, in more detail. Okay. So okay. So if we just talk about what we are going to study today, so it is based on deployable structures basically and over constrained mechanism. Okay, so just in the beginning I want to say, you know already what is degree of freedom and what is the formula for degree of freedom and what does it mean, what do we mean by degree of freedom, right? Then we'll also see over constraint mechanisms, we'll see deployable structures, and so you might have seen in the lecture that Professor Ashitava Ghoshal taught, that how the antennas are folded and then they are deployed in space when required. So you do not have sufficient space to like have a very big antenna and carry it over there. No, it has to be compressed and it has to be deployed in the structure. So these structures are very important. And then what is constraint based modeling? So these topics are extremely important in robotics: space, structures, mechanism, design, etc. Okay. So coming back to just degree of freedom. So what is the degree of freedom? It is basically number of independent parameters required to define the configuration of the system. Right. So let's say if there is a particle in space, then it has 3 degrees of freedom, right? If it is just a particle, it has 3 degrees of freedom, x, y, and z, because it is a point mass. But if there is a rigid body in space, it has 6 degrees of freedom. It has 3 translation degrees of freedom and 3 rotational degrees of freedom, right? And how do you find out degrees of freedom? It is found out using, this is very important, okay, where n is the total number of links, okay, j is number of joints, and fi is degree of freedom of each joint, and lambda is 3 for planar systems, and 6 for spatial systems. Okay. So for example, if there is a planar 4-bar mechanism, so for this, number of links is 4, okay, number of joints is 4, each joint has 1 degree of freedom, and since it is planar, so lambda is equal to 3. So if you find out a degree of freedom using the same formula, you'll find it to be equal to 1. So it is 1 degree of freedom system. Okay. Similarly, if we talk about Puma robot, okay, it has number of links as 7, number of joints as 6, okay. Each joint has 1 degree of freedom, and since it is not planar and is spatial, lambda is equal to 6. So our degree of freedom is 6 into 7 minus 6 minus 1 plus 6 is equal to 6. So it is basically a 6 degrees of freedom robot. So this Gribbler formula is based on counting only. It does not consider the geometry, right? But there are mechanisms where degree of freedom from formula is not equal to actual motion, but system still moves. Okay, so the key idea here is that motion happens due to special geometry. Okay, redundant constraints, passive degrees of freedom. Okay, and what are these called? These are called over constrained mechanisms. Okay, so examples, if we take examples, so I'm not going to draw all of them here, all of them are written described well in the slides, but let's say you have 3 slider mechanism, I think you remember this diagram, right? So there were prismatic joints here, and then its special geometry allows motion. Then you might also remember RPPR mechanism. In this, passive joints exist. Then there are also parallelogram linkage. Where one link is redundant. And there is this Burmester mechanism, which has redundant joint. So even if degrees of freedom calculation gives wrong value, system still can move because constraints are not independent. Okay. So we also saw Bennett's linkage. I won't go into detail. It is spatial 4-hour linkage, and from degrees of freedom formula you get it equal you get DOF equal to -2, which is just a nonsense, but it actually moves. So the special condition which we have there, if you remember from the lecture, sine alpha by A is sine beta by B. So this special geometry enables motion. So over constrained mechanism does not mean it is immobile. It means that constraints are dependent. Okay. So for example, hinged door, there are multiple hinges, but it moves. Okay. So there are, I hope you remember, there are some deployable space structures like that. There is Hoberman sphere, and then there is Bricard linkage, so all of these. Okay. Now, deployable structures are used in satellites, space stations, solar panels. And what is the benefit of them? That they are compact during launch. Okay. They can expand in space, and then they act as structure after deployment. Okay, so if you might have seen pantograph mechanism, it has revolute joints, passive cables, and active cables. The active cables control motion, and the passive cable stops motion and adds stiffness. Okay, so mechanism during motion, but there is actions. It is a structure after deployment. Okay. Now there are types of coordinates. Just okay. Yeah, there are types of coordinates. It is either relative, which is mainly composed of joint angles, and then reference point, and then Cartesian, which are natural coordinates. So relative, reference, and Cartesian. What are the advantages and disadvantages of each of them? It has very few variables. It has physical meaning. It has simple equations. It has non-linear equations. It has large variables. And it has more variables. Okay. Now, about constraints. We have already seen loop closure constraints, right? If you remember. So they are non-linear constraints. Okay. But natural coordinate constraints, for example, if there is some distance constraint, Rij into Rij is equal to some Lij square. It means the distance between 2 points remain constant. If there is 3-point constraint, it can be Rij into Rik is equal to Lij into Lik into cos alpha. So, natural coordinates convert geometry into algebra. Okay. And when we talk about joint constraints, we have spherical joints, which is at the same point, revolute joint, which has axis constraint, and then cylindrical joint, which slides and rotates. Okay. So, let's say we have system constraint as, let's say we have constraints. Okay. If we differentiate it, it would be Jacobian into delta x is equal to 0. Okay. And important point here is degree of freedom is dimension of null space of J. Okay. So what is the algorithm to find degrees of freedom? You add length constraints, you add joint constraints, you add boundary constraints. If null space does not decrease, constraint is redundant. Okay. For example, in 3-slider mechanism, initially there are many constraints, right? Some are redundant. Final degrees of freedom that we get is 1. So Jacobian reveals the hidden redundancy. Okay. So for example, in compass mechanism, we have redundant joint. In Bennett linkage, we have geometry based motion. And in SLE mast, we have redundant links. Okay. Now, when we talk about static analysis, after deployment, the mechanism becomes structured, right? So we have axial stiffness, we have bending stiffness, and we have total stiffness. Axial stiffness can be denoted by Km, bending stiffness by Kn, and total stiffness is basically the sum of Km and Kn. Okay. And how do we define this? So this is Jacobian transpose, some Jacobian transpose. And before that, what is this? Sm into delta L is equal to delta T. Okay. Here also, if you have seen, Jm transpose into Sn into Jm. So total stiffness is given by this. Now, what is the important condition? What is the criteria to detect redundancy? If rank of Ks is equal to rank of Js, then this equality can help us to detect redundancy. Okay. So Grubler formula fails for over constrained systems, right? And Jacobian constrained Jacobian gives correct degrees of freedom. So it helps to detect redundant links and joints. It enables kinematic and dynamic analysis, and it is very helpful in deployable structure. Okay. So basically you understood what is degrees of freedom. It basically tells us how many independent motions the system has. Every rigid body can translate and rotate. It has total 6 degrees of freedom, and we saw Grubler's formula and everything. Then we understood that Grubler formula ignores geometry. This formula only counts links and joints. It does not consider the geometry. Then we move to over constrained system, where degree of freedom from formula is not same as actual motion, but mechanism still moves. So this is the most important idea today. And then the reason is special geometry, redundant constraints, and passive degrees of freedom that we already saw. Okay. And then for deployable structures, I think I should have mentioned. So if So something is compact, it expands and then it becomes rigid. So it is used in satellites where space is limited during launch. Okay. And in pantograph mechanism, you might have seen in the lecture itself. So it is a kind of scissor mechanism where active cable drives the motion and passive cable stops motion and adds stiffness. Initially, mechanism moves, but finally becomes a structure. Okay. About coordinates, I think we are very clear, and about constraints, okay, I think, okay. So we saw the algorithm that we have to add length constraints and then add joint constraints and then add boundary constraints. If nullity does not reduce, the redundant constraint is there. That's how we identify redundancy. And then, okay. So I think I have covered this slide. The thing which needs to be very clear is that, okay, about static analysis also I think it is clear. Km equals to J transpose Smj. So, okay. So I think from here we can move to the questions. I think this lecture was not so long lecture. So the contents are covered. Okay. So I hope this is something that you've seen and you remember. So the degree of freedom of the three slider arrangement shown in figure is shown in figure below as per the Glubner-Kirchhoff criterion. Okay, we want the degrees of freedom. Okay, so what do we use? We'll use degree of freedom is lambda into n minus j minus 1 plus sigma fi. Okay, since this is a planar mechanism, lambda is equal to 3. Okay, now we'll count the links. So from the figure, how many links do we have? We have 3 outer rigid links forming a triangle. Okay. Then we have 3 slider blocks. Each slider is a separate link, right? So hold on, my laptop is not taking charge. Just hold on, I'm looking for charging the laptop. Good to go. So each slider acts as a separate link. Okay. And then we have one ground link. Here it is grounded, you can see. Okay. So in total we have n is equal to 7 because we have 7 links. Okay. If we count the joints, each slider arrangement has, sorry, each slider arrangement has one prismatic joint, which is the slider, and one connection to the link. Okay. So total joints are how many? Can someone tell me?
3.
How many?
3 by 3 by
3.
3. Yes.
Oh,
With the slider.
yeah. It's not 3. So I'll just clarify myself again. Each slider arrangement has one prismatic joint, right? This one, and it has one connection to the link. So in total we have three prismatic joints and three connection to the links, right? So it has to be six. I hope it is clear. Just a second.
Okay, ma'am.
Yeah. So okay, so we have j is equal to 6. Okay, and each joint, yeah, that we are discussing, that is exactly what we are discussing. Each joint as a corner is a revolute joint. So each joint, revolute or prismatic, has 1 degree of freedom. So each joint, so we have 3 revolute and 3 prismatic. Okay, so in total we have 6. So sigma Fi is equal to 6, right? Each one of them contributes 1 degree of freedom. So if we apply the formula, it's lambda is 3 because it is planar. 7 minus 6 minus 1 plus 6, which is equal to 3 into 0 plus 6 is equal to 6. Okay? But wait, this counting is incorrect because each slider each slider connects two links. So joint counting must be done carefully. And this is where your answer was correct. So if we understand it properly, each slider is just one prismatic joint and total joints actually are 3 prismatic joints. Okay, triangle connections are rigid and there are no extra joints. So this mistake shouldn't be made. We don't have to assume that here there are this joints. So anytime you see this figure, this is a very common mistake where people think that this is also joined apart from prismatic. So in that case, what would be the answer? Degree of freedom is 3 into 7 minus 3 minus 1 because now our j is 3 and we are on the correct track. It was just to identify and it was pointed out very clearly. Plus 3, so it is 3 into 3 plus 3, it is 12. Now, is this correct?
No, ma'am.
And why it is not correct?
I think number of link is wrong.
Okay, according to your number of link is wrong. Okay.
Okay. Yes, ma'am. Yes.
Okay, so
ধরে লিঙ্ক একটা হবে
Ma'am, for
এইদিকে
over
একটা হবে
constant mechanism, degree of freedom less
uh,
than 1.
One, less than one, less than zero.
mm-hmm,
So I think
okay,
Our structure
it is
degree of freedom, ma'am, less than zero.
okay, okay. So we'll arrive at the result. 0 is the correct answer and we'll arrive to it. So, okay. So this 3 slider mechanism is over constrained. It has dependent constraints. The formula gives us wrong value. So our actual degree of freedom is not same as computed degree of freedom. Okay, but the question explicitly says as per Grubler-Kajbek criterion. So we must use pure counting without correcting for redundancy. Okay, so if we do proper counting, okay, so in our case, n is equal to 4.
4. Yes.
Okay, triangle is treated as a single rigid loop We have 3 sliders and Fi is 1 each.
Five,
Okay,
one,
so
three.
our degree of freedom is 3 into 4 minus 3 minus 1 plus 3 is equal to 3. But due to constraint dependency, 3 constraints cancel. So effective degree of freedom that you have is 0.
Zero. Yes.
So Grubler counts constraints as independent. Here they are not independent. Okay. So formula says 0 degree of freedom, but actual motion is 1 degree of freedom. So the first option that we have here is my it's plus 1. So it's minus 1. So negative degree of freedom means over constraint, but the counting here does not give negative, so it is wrong. And for plus 1, this is actual physical degree of freedom, but the question as per Glover, so this is also wrong. And then can't be determined is no, it can be determined using the formula. So this is correct. So they are basically testing, did you blindly use the formula or did you mix actual motion versus computed degrees of freedom? So from Grubler degrees of freedom, we get it to be equal to 0, but for actual degree of freedom, it is 1. Okay. Uh, then, as discussed in the lecture, over-constrained mechanisms cannot move since the degree of freedom is less than 1, cannot move since they do not have an actuator, cannot move can move due to special geometry, should not be used since they do not move. Fourth option, I don't know. It is like it should not be the correct answer. Okay, any answer? Any guesses?
Special geometry.
Special geometry you're saying. Okay. Anyone else wants to take a guess?
Third option.
Sorry?
Third option, ma'am. Can move
Okay.
due to special geometry only.
Okay. That's correct. Both of you are correct. Good. So, over-constrained mechanisms are systems where the Grubler formula predicts degrees of freedom to be less than equal to 0. But in reality, the mechanism still moves. Why? Because some constraints are not independent. They become dependent due to special geometric relationships. So, motion exists because of a specific geometry condition. For example, we saw sine alpha upon A is equal to sine beta upon B. So, this reduces the effective constraints. So, although the number of constraints seem large, some constraints overlap due to geometry, allowing motion. Okay. So, the options that we have are cannot move since the degree of freedom is less than 1. It's wrong because Grubler degree of freedom is misleading here. Over constraint mechanisms do not move despite degrees of freedom less than equal to 0. This is a main misconception this topic is trying to break. Okay. Then in option 2 we have, it cannot move since they do not have an actuator. It's wrong because motion is not about actuator presence. Even passive mechanisms can move if constraints allow motion. So actuator is not same as mobility. Okay. And then the fourth option is it shouldn't be used since they do not move. It is completely wrong because these mechanisms are widely used. Examples are deployable structures and Bennett linkage and space mechanisms. So they are highly useful engineering systems. So this option is also wrong. Okay. So they are basically again checking if you're believing Grubler blindly. You should understand constraint dependence versus independence. Okay. So over constraint mechanism does not mean it is immobile. Motion exists due to special geometry. Okay. So this question is about Bennett linkage. So question is the well-known Bennett linkage shown in figure below as degree of freedom of -2 according to Grubbler-Hutchback criterion has degree of freedom has degree of freedom as 1 since it is similar to planar 4-bar linkage, can move when the angle alpha and beta are related as the following, and link lengths are A1, A3 is equal to A, A2, A4 is equal to B, see the above figure, okay, and can move when adjacent sides are equal. So, okay, so if we find out the degrees of freedom using Grubbler's criteria, this is a spatial mechanism where lambda is equal to 6. The links are 4 in number, joints are 4 in number, and all of them are revolute joints, right? And each joint has 1 degree of freedom. So, Fi is equal to 1. When you apply the formula, it is 6 into 4 minus 1 plus 4, right? Which is 6 into minus 1 plus 4, which is minus 2. So, Grubbler predicts degrees of freedom to be equal to -2. So, this is the correct option, right? Now, negative degrees of freedom means system is over-constrained, right? But does it move? Yes, this is the famous Bennett linkage. It moves because of special geometric conditions. Okay. And what are those required conditions? They are that opposite length link should be equal in length, like A1 and A3 should be equal to A. Okay. And A2, A4 should be equal to some number B. And the angle condition they have is sine alpha upon upon A is equal to sine beta upon B. So these make constraints dependent, so motion becomes possible. Okay. So the other option that we have are has degree of freedom as 1 since it is similar to a planar 4-bar linkage. It is wrong. Why? Because Bennett linkage is spatial, not planar. So if we have planar 4-bar, it is 1 degree of freedom. Bennett is over-constrained spatial system. So superficial similarity is there, but it is not the same degree of freedom. Okay. Then in the fourth option, we have can move when adjacent sides are equal. It's wrong because the correct condition is opposite sides are equal and not adjacent sides are equal. Also, angle relation is mandatory. So just equal length is not sufficient, although equal length के बारे में भी गलत लिखा है. But then angle relation is mandatory. So they test if you are confusing so this question basically tests if you are confusing planar 4-bar mechanism with Bennett linkage. Okay, you might mark it to be equal to degree of freedom equal to 1, and if you forget the angle condition, this is also problematic. So length equality is not enough, and thinking negative degrees of freedom means no motion is completely wrong. Okay, so yeah, as we saw in earlier question, actual motion exists due to special geometry, and Bennett linkage is a perfect example of constraint dependency, right? Okay, let's move to the fourth question. The main reason why deployable structures are used in aircrafts is they have less than 1 degree of freedom and thus do not need an actuator, or once deployed and the actuator is locked, it can withstand external loading. They can be kept in a compact form in the payload housing, and they are very easy to manufacture. Okay, so deployable structures are mainly used in spacecraft because of 2 key requirements. One is compact storage, right? Because you have lack of space during launch. Space inside the rocket or payload bay is very limited. There are large structures which are solar panels, antennas, and they cannot fit in full size. So they are folded, compact initially, then deployed in space. Okay. Second thing is, structural strength after deployment. So after deployment, actuator is locked. System becomes a rigid structure. it must withstand external forces. If there are some vibrations or some loads which are acting on it, all of them should be taken care of. Okay, so mechanism, this is the mechanism during motion, but it is structure after deployment. Okay, so what are the two correct options? Is once deployed and actuator is locked, it can withstand external loading and they can be kept in compact form in the payload housing. The other options are uh, they have less than 1 degree of freedom and thus do not need an actuator. Wrong, because deployable structures typically have 1 degree of freedom during deployment. They require an actuator to unfold. So degree of freedom less than 1 does not eliminate the need of actuator. Okay. The fourth option is they are very easy to manufacture. Wrong, because they are actually complex precision systems used in space. High accuracy is required. So ease of manufacturing is not the reason for using them. So this is also wrong. So basically you should know what is the real engineering motivation versus what are the theoretical statements. You shouldn't only focus on degrees of freedom and you shouldn't ignore the space constraints and structural function. So deployable structures are used because they are compact during launch and they are rigid and load bearing. They have load bearing capacity after deployment. Okay. Let's move to the next question. A deployable structure made with planar Caesar-like elements consists of several SLEs stacked on one top of another, is actuated by a cable which is shortened by a motor, consists of passive cables which can terminate the deployment and add stiffness to the structure, will deploy till the deployment angle reaches less than 45 degrees. Any guesses?
B, C, and D में.
You say B, C, and D.
And
Okay. Anyone else?
All are true.
Sorry?
All are true.
Okay. According to you, all are true. So, okay. So, yeah, all of them are correct answer. Okay. And let's see why all of them are correct. So, what are stacked SLEs? So, it is basically a deployable mast which is made by repeating Caesar-like elements and we stack them vertically. This increases the height during deployment. Then, what is this actuation by cable? So, it is typically one active cable which is controlled by a motor. As cable shortens, the structure expands. This drives the deployment. Okay, so this increases height during deployment. This drives the deployment. And then the third option is about passive cables. Passive cables are slack initially, become tight at the full deployment. So the functions are it stops further motion and it increases the stiffness. And about deployable angle limit, deployment angle varies from 0 to 45 degree usually. So correct option is less than 45 degrees. And uh, so if you ignore this, it can be problematic because if option said only 45 degree, it is wrong. But if it is less than equal to 45 degrees, it is correct. You shouldn't forget the role of passive cables. They are important. Okay, it's not just that active cable matters. Passive cables also matter. So SLE based deployable structures are modular. They are stacked. They use active cable for motion. They use passive cables for locking and stiffness, and they have limited deployment angle. Okay. So the reference point coordinates for a planar link are typically less in number compared to relative coordinates. For a planar link are typically less in number compared to Cartesian coordinates. For a planar link are 3 in number, gives rise to at least number of loop closure constraint equations. So what are the correct options? What are reference point coordinates? What do we define for each link? Okay, so let's start from there and then we'll come to the options. Okay, so for each link, we define position of reference point, okay, which is x comma y, and orientation, which is phi. So for a planar link, the coordinates are x, y, and phi. Hence, we have 3 coordinates. Okay. So for a planar link, they are 3 in number. This is correct, right? Now, comparison with Cartesian coordinates, which are natural coordinates. Was right. So they use coordinates of multiple points on the link. They are typically more variables. There are typically more variables here because they use multiple points of the link. So if you see from lecture, there were 9 variables, 6 variables, 3 variables, and 6 variables for Cartesian, 9 for reference, and 3 for relative. So for a single link, in reference, we have 3 variables. We saw that, right? But in Cartesian, we have usually more. Okay, because multiple points are tracked. So reference coordinates are less than Cartesian. Okay, the other option is for a planar link, they are typically less in number compared to relative coordinates. It's wrong because relative coordinates use minimum variables. Example, joint angles only. So for relative it is less, and then we have reference and then Cartesian. Okay. And in the last option it is gives rise to least number of loop closure constraint equations. It is wrong because relative coordinates give least constraints. Reference coordinates require more constraints. Okay. So if you remember from the lecture, for relative constraints we had least equations, and for Cartesian algebraically simple equations were there, but there were more equations. Okay. So if we talk about order of coordinate efficiency, okay, relative is best, then we have reference, and then we have Cartesian, sorry, which is largest. So for a planar link, the reference coordinates are 3, more than relative and less than Cartesian. Okay. The loop closure constraint equations using natural coordinates contains terms which are only linear in the coordinates, contains terms which are only quadratic in the coordinates, contains terms which are at most quadratic in the coordinates, contain terms which are transcendental. Okay. So when we use natural coordinates, constraints are written using distance equations. We are talking about natural coordinates. They are written using distance equations and also in dot products. Okay. So an example of distance constraint is x1 minus x2 square plus y1 minus y2 square is equal to L square. This is quadratic. Yeah. And when we talk about dot product, It's x2 minus x1 into x3 minus x2 plus y2 minus y1 plus into, sorry, y3 minus y. This is also quadratic. So key observation to me here is there is no sine, cosine or transcendental function. There are only polynomial terms and the highest power is 2. Therefore terms are at most quadratic. Okay. So the first option is contains terms which are only linear in the coordinates. It's wrong because squared terms exist like x square, y square, they exist. So it's not purely linear. Okay. Second option is contains terms which are only quadratic in the coordinates. Wrong because some terms are linear. For example, these differences. These are linear. So not all terms are quadratic. So only quadratic is too strict. Okay. And yeah, this is correct. This we already saw. And the fourth option is contains terms which are transcendental. There is no sine term, no cosine term, no exponential term. Those appear in relative coordinates, not natural coordinates. So this is also wrong. So for relative coordinates, it has to be trigonometric and it is transcendental. But for natural coordinates, it's polynomial. It is at max quadratic. So natural coordinates are simpler equations, no trigonometric functions, at most quadratic terms are there. Okay. I hope the idea is clear. We'll move to the next question. The constraint Jacobian matrix is obtained from the derivative of constraint equation, contains only terms linear in the natural coordinates used to model the mechanism, has the least number of elements when natural coordinates are used, is always square for over constraint mechanism. How is the Jacobian formed? We start with constraint equations, right? Fj x1, y1, etc., etc., etc. is equal to 0. When we differentiate, we get Jacobian to delta x is equal to 0. So Jacobian is the derivative of the constraint, comes from the derivative of constraint equation. Okay. Why are terms linear? So constraint equation or natural coordinates are at most quadratic. Okay. Now if we differentiate, so for example, x1 minus x2 का square का differentiation करेंगे, we would get 2x1 minus x2. So after differentiation, we are only left with linear terms. Therefore, Jacobian contains only linear terms. Okay. So, is obtained from derivative of constraint Jacobian is correct and contains only terms linear in the natural coordinates used to model the mechanism. Okay. So, we saw it is the constraint equations using natural coordinates are at most quadratic, and if we differentiate it, it's going to be linear. Okay. So other option is has the least number of elements when natural coordinates are used. Wrong, because natural coordinates are use more variables. So Jacobian becomes larger and does not become smaller. So if there are least variables, it's in relative coordinates and not in natural. Okay. So this is wrong. And then it is always square for an over constraint mechanism. Wrong because Jacobian size number of constraints into number of variables. For over constraint system, constraint is greater than degrees of freedom, right? So matrix is usually rectangular and not square. So this is also wrong. So yeah, what was important here, you need to connect quadratic constraints to linear Jacobian and natural coordinates to larger system. So finally we can say that constraint Jacobian comes from the derivative of Jacobians, contains only linear terms and not necessarily square and not minimal in size. Okay. Just hold on for 1 minute. So the next question is, For the constraint Jacobian matrix, the dimension is same as the degree of freedom. The rank is same as degree of freedom. If the nullity does not change when a constraint is added, the constraint is redundant. If the nullity does not change when a boundary condition is added, the boundary condition is redundant. Okay. So for the Jacobian matrix J, right? So what is nullity? Nullity of J is dimension of solution space. Which equals degrees of freedom. What happens when we add constraint? So adding a constraint means adding a row to the Jacobian. Okay. There are two possibilities. Could be that the constraint is independent. Okay. So in this case, nullity decreases and degrees of freedom reduces. The other case can be constraint is redundant and nullity does not change and degrees of freedom remains same. Okay. So if nullity does not change, constraint is redundant. Okay. So the correct option here is if the nullity does not change when a constraint is added, the constraint is redundant. Let's go with the other options. The first option is the dimension is same as degree of freedom. It's wrong because dimension of matrix is not equal to degree of freedom. Degree of freedom is nullity and not matrix size. So it is wrong. And then the rank is same as degree of freedom. It is wrong because degree of freedom is nullity of J, which is n minus rank of J. So it is wrong. Rank is not equal to degrees of freedom. And the fourth option is the nullity does not change when a boundary condition is added. The boundary constraint is redundant. Subtle but wrong because algorithm says check redundancy during constraint addition. Boundary conditions are treated separately at the end. Okay. So yeah. So this is also incorrect. So do you remember exact algorithm wording? You should go and see it again. Okay. If nullity does not decrease, constraint is redundant. Okay. And also remember degree of freedom is equal to nullity of J. Okay.
Ma'am, in last option,
Yeah.
when we added boundary constant,
Yeah.
so boundary constant is redundant, but here added boundary condition.
So the option says if the nullity does not change when a boundary condition is added, the boundary constraint is redundant. So
Ma'am, if a boundary constant is added, then
uh, what is the
boundary
difference
constant is
between boundary condition and boundary constraint? The boundary condition that you are adding would ultimately go as constraint, right? So for example,
but in lecture slide boundary constant is added, but nullity does not nullity decreases and boundary constant is redundant.
so you're saying they have used constraint word here?
Yes.
So that's what I'm saying. So see, if you let's say have a system, okay, let's say I have some system, be it just a motor, and then if I have some boundary condition such that when boundary condition could be like if I talk about it in terms of time, it can be any initial condition and any condition at some point of time. Okay, so for example, just let me think of an example. Okay, so let's say you're modeling a robot. Okay, it has, it is some two-legged robot. Here you have a constraint, and what is your constraint? The constraint is that the this corner of the robot should not get detached from this leg ka this point. Okay, so this is a boundary condition. It is not condition in time, but it is a special condition. Okay, so that saying that this should not get detached is something that you're imposing. Now how would you use this boundary condition? My boundary condition is, let's say here if it is x, I use a rotation matrix, I come at this point, and for leg also I have defined some coordinate system, and then I say that x of torso, let's say I'm saying that it is shifting by whatever, by plus something, is equal to x of leg. If I am saying this is my boundary condition, but how am I going to use it in the system? It's going to be through a constraint. I'll bring this term also to this side and make it equal to 0, and this would be a constraint to the system. Okay, so all boundary conditions are constraints. Does that make sense? Did I get your question correctly? Arnab, I cannot hear you.
Okay,
So, okay,
okay, ma'am. Okay.
okay,
And
thanks. Okay, so in a Kempe-Burmester mechanism shown in the figure below, the link QD is, this is directly from the slide, the link QD is redundant, joint D is redundant, joint Q is redundant, none of the joints are redundant. Okay. If you remember it, it's just about when you have read the lecture. In the Kempe-Burmester mechanism, constraint Jacobian analysis shows that the joint at D is redundant. So what does the redundant joint mean? A joint is redundant if removing it does not change the motion. Constraints it imposes are already satisfied by another other constraints. So if you remove it, does not change the motion. Okay, and then the constraints it imposes are already satisfied by other constraints. Okay, so what happens here? Even if this joint D is removed, the link CD can rotate correctly. Motion of the mechanism is unchanged. Why? Because other links already enforce the same constraint. So constraints at joint D are dependent on other constraints. So the first option is the link QD is redundant. What is QD? This one. Okay. It's wrong because the link itself is needed. Only the joint constraint is redundant. Okay. So important distinction is between joint and link and joint redundancy. You should understand and pick the option correctly. Okay. Second option is the joint. Did I mark it wrong? Yeah. The joint Q is redundant. It is wrong because joint Q contributes essential motion constraint. Removing it changes the mechanism behavior. So this is also incorrect. Last option is none of the joints are redundant. It's wrong because the mechanism is over constrained and at least one constraint must be redundant, and it is it. So yeah, you have to basically understand. जहाँ पे redundant link की बात हो रही है या joint की बात हो रही है, don't move to the opposite side. So okay, removing a joint and removing a link are not the same. Okay. So joint D is redundant, constraints are dependent, and motion still exists. Okay. Okay, let's move to the next question. In the kinematic analysis of over-constrained mechanisms, the motion of the links can be simulated only after redundant joints and links are identified, can be simulated without obtaining the redundant links and joints, are independent of the actuator, are independent of the geometry of mechanism. Okay. So, the workflow for over-constrained mechanism is, there are certain steps that we need to follow, right? We need to identify redundancy. Okay. And then, so how do we do that? We use constraint Jacobian. We find what are the redundant joints, what are the redundant links. In step 2, we remove redundancy. Okay. Conceptually, because we only keep independent constraints. And in third, we perform kinematic analysis. This is only, after doing this kinematic analysis only, now the system becomes consistent and solvable. Okay, so you identify redundancy, you remove redundancy by keeping only the independent constraints, and then now your system becomes consistent and solvable when you do kinematic analysis. Why this is necessary? Because if you do not remove redundancy, system becomes over-constrained mathematically, equation become inconsistent or dependent, and simulation may fail or give incorrect results. So you must identify redundancy before simulation. Alright, so the correct option is the first one, right? In the second option, we have can be simulated without obtaining the redundant links and joints. It is wrong because it is an over-constrained system and then there are dependent constraints. So it leads to incorrect or unsolvable equations. The third option is are independent of the actuator. It's wrong because motion depends on actuation input. Without actuator, no controlled motion is possible. And the last option is they are independent of the geometry of mechanism. This is completely wrong because geometry is the main reason motion exists. Over-constrained motion happens due to special geometry. Okay. So, did you understand the correct sequence? You can't solve directly. You have to remove redundancy and then solve. So, for over-constrained mechanisms, identify redundant constraints, remove the dependency, and then perform the simulation. Without first step, which is identifying the redundant constraints, the analysis fails. All right. So, okay. This is the last question that we are taking up today. So, here we have, just a second. Okay. So, in the static analysis of over-constrained mechanisms, the rank of the stiffness matrix is less than rank of the Jacobian matrix. The rank of stiffness matrix is equal to the rank of Jacobian matrix. The stiffness matrix is more than the rank of Jacobian matrix, and the stiffness and constraint Jacobian matrix are not related. This we have already discussed, right? So, the stiffness matrix, right, is given by Jacobian of the stiffness and then SS and JS, where your JS is constraint Jacobian, right, and SS is element stiffness matrix. Okay, so if we apply the rank, so from here rank of A transpose A is equal to rank of A, right? So if we apply the same logic here, your rank of KS should be equal to rank of JS. So stiffness matrix and Jacobian have the same rank. Now, rank tells, what does rank tell? It tells the number of independent constraints and the number of load carrying directions. I think I should write this. Okay, and if redundancy exists, the rank reduces. Structure has mechanisms or flexibility. Okay, so the other options are stiffness matrix is less than the rank of Jacobian matrix. It's wrong because the rank is exactly equal, not less. And then the other option is stiffness matrix is more than rank of the constrained Jacobian matrix. It is wrong because it cannot exceed rank of Jacobian. It is derived directly from it. And the last option is stiffness and constrained Jacobian matrix are not related. This is completely wrong. They are directly related. Stiffness is constructed using Jacobian. So this is also incorrect. So what is being tested here in general is, do you understand J transpose Sj has the rank of J? And if it is equated to rank on Ks on the other side, then it has to be equal to rank of Ks. Okay. So your rank of Js is same as rank of Ks. It is used to detect redundancy, analyze stiffness, and understand the structural behavior. Okay. So with this, we end today's lecture, and today it's the last lecture. I hope you have got a chance to learn much from this course. I hope the tutorial sessions that I am taking were helpful in understanding the concepts and solving the assignments. So one thing, Arnab, there was a day when you had some question and I had asked you to post on discussion forum. Like, I went to the discussion forum, but I could not find your question. So it's in a general way, I am saying that if any of you have any confusion, you can clarify all your doubts either here, because if here sharing becomes difficult, you can post it in discussion forum. I'm active there. If there is a question, I'll be happy to answer. And regarding all the exam questions and technical and logistic questions related to how is it going to happen in exam or mock test and everything, that is the best place to post, because NPTEL team is there. I'm not aware of all these because I am just a teaching assistant for this course, and I'm supposed to tutor you when you after you see the lecture. But in case you have any question and you want to know something, please post on discussion forum. I think your exams are really near. It's on 18th April, I suppose.
Yes.
I'm not. Okay, okay. So if it is like that, you post all your questions over there and we are there to answer your queries. All right?
Hello.
All not.
Ma'am, one question
Yeah.
from assignment 4. For a 4-bar mechanism, L0 equal to 8, L1 3, L2 8, L3 4, and A equal to 4 and B equal to 4. That's when a coupler curve is broken with L2 equal to A plus B. The coupler curves obtained will interact at how many points? How can we find out
So
intercept?
I think I can send you the solution for this assignment, for this question. Uh, can you post it on discussion forum? I'll look at it just after the lecture, after this.
How?
Sorry?
Post करो.
Do you know how to post it on discussion forum?
No,
Or
ma'am.
oh, you don't know. That is why I did not find. Okay. So all your okay, okay. Just hold on, let me uh, where do I have it saved? So, okay, just let me share my screen. I'll take off the screen. Uh, okay, let me go to Google Meet. I have to present my entire screen. I hope my screen is visible to you now. Yeah, so what you have to do is you have the link, right? You can just log in here. After login, when you log in here, when you go to course, um, when you come here, you have to, I think, click on question and answer. Just let me check. Yeah, click on question and answer. You'll be directed to Google discussion forum, okay? Where you can discuss all your queries. Your faculty also sits here, as well as the other of students of the course are here. VTAs are there. Everyone is here because all of us have the login to this, okay? Just click on Q&A and click on continue. Once you click on continue, you are directed to this page, okay? And you can see if your questions that you had, if they are already answered. For example, someone has asked what is the question paper format, okay? And this reply is given by Pramod Pal. He is also a TA, like he is not teaching, but he is managing the things internally. So yeah, he asked for upcoming question paper, and he has said that all will be MCQ format, and there won't be any subjective or long type questions, I think. So all of these logistic details are not with me, but they are with people coordinating this course. Okay, so another question is regarding this mock exam features. So in the final exam, all the questions will be MCQ type. Most of the question will be from assignments and lectures. That is what is answered. So people are viewing it as well. So you post your question here and we'll be answering. Since I know that you have a question here, please post the screenshot of the question. Don't copy the question and write it because the text gets distorted. So just post the question as screenshot and I'll answer it there itself. All right.
Okay, ma'am.
Yeah, and look through all the questions that have been asked here. It will be helpful for all of you. If you're posting it right away, I'll see it by tonight or max by tomorrow morning. Okay, any other questions? If any other person also has question here, sorry.
वो बनाना है ना मेरा टॉपिक डिसाइड है बस उसे वो यार कर ही लोगे
Ma'am, till now I am not getting admit card for the examination. When it is possible?
Exam
Hello.
is on 18th, right? I am not sure when it would be released to you, or it might have been released. I'm not aware of that. Can you
Okay.
again post this here so that the
Okay.
relevant people can see if it has been already sent out to the public? Then if you have not received it, then it is a problem and you need to communicate here. And if it has not been sent, it will definitely come to you. So I would request you to kindly raise this question here, or any other question that you have related to the exam, please raise it over here. We will answer. You can see here NPTEL also answers the question and VTAs also answer the questions. Okay.
Okay. Okay, ma'am. Thank you. Okay.
Thank you, ma'am, for guiding us. Thank you so much.
Thank you so much. This was my course.
Thank
I
you.
was taking this course for the first time. I had taken control systems course, advanced robotics course, but this course I was taking for the first time. I really feel glad in interacting with you. Some of the faces I have known for days now, because I have almost met you guys in every lecture, and I'm really happy if the teachings were of help to you, either in solving the assignments or understanding the concepts, and hope you are motivated to take robotics in future. You should always have understanding, fundamental understanding is very important. This was an advanced concept, but you should also know introduction to robotics course completely. You should understand all of these. You should understand how to deploy it. You should always remain up to date with what is going on in robotics, because making fundamental is good, like working on fundamentals is good, but apart from that you should also be understanding what is going on in the world and what pace the things are moving really fast in robotics. Okay, so work on all of these. For the exams you have to study all of these, and that is good. You get to build your fundamentals, but also practice coding, practice electronics, practice robot manufacturing, practice deploying it in real world, practice doing something good for the like novel things that people haven't done. Okay, so yeah, that is my advice for all of you who are here, and for everyone who would be watching the recorded lectures, just in case. But I would suggest you to take this seriously. If you have learned this much, please don't break the momentum. Learn even more. Never let the quest of learning die inside you, and you all will do something good. All the best for your exams and for your life ahead.
Okay, man.
Thank
Thank
you,
you.
ma'am.
Thank you,
Okay.
ma'am.
Yeah, sure. Bye.
Good night, ma'am.